Yeah, today's video comes by way of request. Someone took me up on my offer and asked in the comments if I could cover Docker resource constraints. So let's dive into that. We're going to look at memory constraints and CPU constraints. I don't have any GPU, so we probably can't demo that, but at least we'll get a feel of what it looks like when you set memory or CPU constraints when you're executing your Docker images. If you like where I'm going with this video, please feel free to drop a like. If you want to see more videos like it, please consider subscribing. And if you want to see something that I'm not covering, consider adding a comment. Tell me what you want to see. I am taking suggestions. Docker is open by default. And so Docker containers will use as many resources as they want, regardless of what else is running on your system. So if you don't set resource constraints, Docker can and will use all the resources on your system, whether it's your personal laptop or your server running in the cloud. The first thing that we're going to look at is this memory constraint, and we're going to set a limit on how much memory our Docker container can use. In doing so, we're basically going to set a kill switch so that if we hit that memory limit, the container will die. What we're going to do, we'll set this memory flag and we will pass in a certain value. We'll say, here's how much memory we're going to allocate. Once the container goes above that, it will get shut down by the system. If you just want to see the code, you don't want to watch the full video, that's fine. I've got a link in the description that's going to point you to the repo where you can find all this code, and the images that I'm using, they are public, so you can pull them anytime, right? All the instructions are in the README. Right now we're looking at some code that I put together to mimic an out of memory error, right? This is to mimic what a memory greedy application would look like if it was running in your container. Right, we start off with just a ticker that's got a, hey, starting at 1, great. And we've got an empty, I think in Python it's called a list. Maybe it's still an array. I don't know. I'm calling it an array. Sorry about that. Anyway, we've got this empty array. And when we enter into this loop, we're going to append 100,000 single item arrays into this array. After it's been added, we'll print, here's how many times we've added, right? So this will increment every time we go through the loop. Great. So I've built this into a Docker image. So let me run this container and I'm going to set 128 megabytes of memory, and we're going to see just how high this ticker can go. All right, I'm removing the container once it's done, 128 megabytes of memory right here, right? So I'm passing in the memory flag, and that's going to limit us to a certain amount, 128 megabytes. All right, so I run it, and it got through 326 iterations before it died, right? The system shut it down because it ran out of memory. Okay, let's see what happens if I drop that down to 64 megabytes of memory. Only got through 160. So we're seeing kind of a pattern. There's a bit of a linear correlation. What happens if I take that up to 256 megabytes? There we go. I think we probably all know what's going to happen. It's going to double the original run, right? But let's find out. So we keep going to, 660. So we're kind of seeing this linear progression, right? The more memory you give it, the more stuff it can store in memory. Pretty straightforward, right? Cool. Let's move on to CPU. CPU is a little more complicated because if you run out of CPU, you won't actually see your container shut down. It will just slow down. So CPU works with this flag, -- CPUs, and then the value, how many, right? What number of CPU cores you want to allocate to your process. That's a shorthand way of writing these two flags, CPU period and CPU quota. CPU period, by default, sets to 100,000 microseconds, which is the same as 100 milliseconds, or a tenth of a second, right? What that means is we're looking at how much CPU power to reserve for your process, your running process, right? That's happening in this container every tenth of a second, okay? And the quota is the number of CPU cores per period, right? So if I say, give me 1 CPU, right? What that actually means is 1 CPU core reserved for a tenth of a second. That's what this shorthand flag means. It's just a shorter way of writing these two flags together. All right, let's see what that looks like in action, because it's not going to shut down my container. Instead, it's going to slow things down. This time, we're going to look at a different file that I've got to mimic CPU utilization. So we've got this worker function that we're going to ignore for just a second. Down here, I'm going to snapshot the start time. I'm taking in a multiplier string from the environment, and the default value I'm setting on that is going to be 1. And then we'll take a look, right? Make sure first, is it a valid integer, right? Is this string convertible to an integer value? Great. If it's not, we throw an error. Makes sense. From there, we have this if statement. If I pass in a multiplier of 0, that is a string of 0. What we're going to do is we're going to spin up a single process, just one. If I pass in any other number, we're going to spin up multiple sub-processes. And the amount of sub-processes is calculated by the amount of CPUs running on the system, right? I've got a Mac M1, so I've got 10 CPU cores. So I can tell you on my machine, CPU count right here is 10. It's going to be different on every machine. This is why this requires some explanation, is because there's no standard way to run this. You're not going to see the same results on every machine. So the CPU count is analogous to the amount of cores running on your box. Then we have the multiplier. So if I have 10, which I do, right, and I pass in a multiplier of 2, it's going to spin up 20 sub-processes, right? If I pass in a multiplier of 8, it will be 80 sub-processes. So when we get down here, right, this is where we actually start up the processes, and each process is going to count to 10 million. We're going to start at 0. We're going to do a super trivial calculation just to make sure we're actually using some CPU, and we're going to increment that counter. Each process will count to 10 million. That's a lot of CPU if we're using more processes than cores. Remember, we won't get shut down. It's not like memory where if you overutilize the amount of CPU, you get shut down. Instead, we will see slowdown. The more CPU we're using or trying to use, the more delays, the more traffic jams there will be on that CPU, and we will slow down our processes. And we're going to see that in action. At the end, we're going to come down here, we'll snapshot the end time, and we'll figure out what the elapsed time was. So how much time it took however many processes for all of them to count to 10 million, right? Incrementing 1 plus 1, 10 million times. So I'm going to come into my terminal. Come on, buddy. There it is. And I'm going to paste in a starting point here. I'm going to allocate 1 CPU, and I'm going to set my process multiplier to 2. So I have 10 cores. That means I'm going to spin up 20 processes. On your computer, it might be different, right? It all depends on your CPU, right? How many cores are in your chip. And this is the image I'm going to run, this Docker CPU simulator. Again, this is public. Anyone can pull this down. Let's see what happens. So it's running and should take 5-ish seconds, 6-ish seconds. Wait, more than that apparently. 10 seconds for 20 processes. That's a really longer time than when I was putting this together. But okay, so it took 10 seconds for 20 processes to make 10 million calculations. That's a lot, right? Let's see what happens then if I bump the CPU up to 3. Will it go faster? The answer is yes. And there we go. Instead of 10 seconds, it took 2.9 seconds, all right? What happens? Remember, I've got 10 cores. What happens if I give it 8? 8 cores. Should go super fast, right? Yep, 1.2 seconds for 20 processes to make 10 million calculations. All right, we've been running with this 20 thing for a while. What happens if I bump this to 10, right? I've got 10 cores. I'm using 10, I'm passing in a multiplier of 10. That's 100 processes running on 8 CPUs. Remember, it was 1.2 just a second ago. What's it going to look like now? 5.3. So we can see the more processes, that is, the bigger the traffic jam, the slower the output, right? CPU won't get shut down, it will just slow down. So the more CPU you provide to your processes, the faster they'll be able to make all these calculations and the less of a traffic jam they'll have. On the other hand, that means less CPU available for other processes. To be honest, when I actually tested this out as I was putting this together, this all went a whole lot faster because I've got other things running on my system now. I've got Golang, PyCharm, WebStorm, WebEx, right? I've got all these things stood up that I use in my daily life at work, and so they're soaking up CPU in the background. That's why this is way slower than what it was when I put this together earlier today. What happens if I just want to run one process? Right? Is there a possibility that I can overpower that process with CPU? The answer is yes, there is. So remember, if I pass in a process multiplier of 0, I'm just going to run one process. Right? A lot of people don't necessarily use multiple processes, right? They might use threading. So let's just see. I'm going to pass in 2 CPUs and I'm going to say run one process by passing in that multiplier of 0. Okay. Let's see how long this takes. 0.37 seconds. What if here, I'll clear this out. What if I pass in 8 CPUs? 0.34 seconds. Not a huge gain. In fact, that's kind of within the standard deviation. You're going to get variable fluctuations in times, right? 0.03 of a second isn't that big of an impact. And I wonder, if I run it again, will I see, okay, about the same thing. What if I pass in 1 CPU, right? What will happen then? Is it that much of a difference? It's not. It's actually the same, right? 0.34 seconds to finish the entire process, for one process to count to 10 million. So what I'm seeing right now is I've hit a ceiling in terms of performance of what my CPU calculations can do. I won't get any higher than this. No matter how much CPU I give this, I will not get any faster, whether it's 1 CPU or 8 CPU. And this is where we can get into over provisioning the CPU for our Docker containers. So let's play with it a little bit. Let's see what happens if I pass in 0.5, right? Do I get a slowdown or does it still hit 0.34? Okay, now I saw a slowdown. Now I'm at 0.7. So I know somewhere within that, somewhere between 0.5 and 1 CPU, that's my sweet spot where I'm gonna hit optimal performance and not waste any resources, reserving CPU for an image that doesn't need it. Be sure to try these flags out on your own. Be sure to try and optimize your resource usage for your Docker container and see if you are hitting that performance limit. And if you like this video, please feel free to drop a like. If you want to see more videos like it, please think of subscribing. And if there's other things you want to see that I'm not covering, leave a comment. Let me know what you want to see. I am taking suggestions.